Okay, so section 9.4 is all about mathematical induction, and induction is one way to prove things. It's different than your two-column proofs in geometry. I'll try to make some kind of remarks about, like, remember this from geometry, this is kind of like that thing. But it's just a different formatting of a proof. And it's more like what you would see in real mathematics. So I don't know if you've ever like tried to Google anything about math before you had a question about something, and then when you Googled it, some kind of proof pops up. It's not always a proof by induction, but I think you would find that a lot of times the proofs you find on the internet are more about like reading and stuff like that than a two-column proof. So more like a paragraph proof or something like that. Before we get into the actual proof method, we need to do a little bit of practice with finding S sub k plus 1. So, do you agree, based on our warm-up, that capital S represents the sum of a series? Are we okay with that? Okay, so that's what our proofs by induction are going to be. We're going to be doing sums of series. Not all proofs by induction have to be for sums of series, but because that's what we learn in Chapter 9, that's where they're introducing proof by induction. That's the types of proofs that we're going to be doing. Okay. So I give you up here two S sub k's. Okay. Now let's look at this first one. S sub k equals 6 divided by k plus 2. What would you do if I asked you to give me S sub 5? And you knew what S sub k was? You plug in 5 everywhere you saw. Okay, so it would be 6 over 7, right? What if I asked you to do S sub 1000? Still plug it in. What if I asked you to do S sub b? You'll plug it in, right? 6 over b plus 2. So what if I'm asking you to do S sub k plus 1? Plug it in, right? Nothing is different, nothing changes. I'm just going to plug in k plus 1 where I see k. And in this instance, k plus 1 plus 2 is really k plus 3. So S sub k is 6 over k plus 2. S sub k plus 1 is 6 over k plus 3. I could do the same thing for my next example. One thing that changes to my next example is I've got more k's. Well, if I have more k's, that just means I have more places to plug in k plus 1, right? So I don't have any k's in my numerator, so my numerator is going to remain 3. This first k, if I do S sub k plus 1, is going to turn into a k plus 1. And then I'm going to be multiplying that by k plus 1 plus 4, which is really k plus 5. And there's my S sub k plus 1. Now, you don't have to do a lot of like extra work with S sub k plus 1. You can decide in your proof if you need to distribute, FOIL, do any of those kinds of things. But just so that you can see what S sub k plus 1 is, you just kind of like simplify. Like if you can add things, you should. Okay, and there will be some times where you'll want to distribute, so you could add like terms. But this is fine. You don't have to write the denominator as k squared plus 6k plus 5. So with your small group, see if you could get these two S sub k plus 1s for me. And notice I introduced exponents there. So remember my statement just now, you don't have to do the extra work. So you don't actually have to square it. You just have to sub in your k plus 1. See what you can get for those. See if you'll agree with your people nearby. If you haven't already, share out with your group members real fast. I'm going to write my answers on the board, but for the ones that you finished, do you agree or not? So can you talk to your partners? I should hear talking. I only hear Tom.
Yep. All right. Okay, did you like do any kind of work for this, or did you do like
Okay, and then after you're done chatting with your group, take a peek at the front board. Do you agree, disagree, have questions? I will say this. If you were to like FOIL out the top, k plus 1 squared, k plus 1 times k plus 1, and write k squared plus 2k plus 1, that's fine. If over here on the second one, you distributed this 3 and called it 3k plus 3, totally fine. So it's not wrong to do that extra multiplication as long as you do it correctly. It's still what s sub k plus 1 is. It's just a matter of when I'm trying to find s sub k plus 1, I generally just leave it alone. Now, we're going to see s sub k plus 1s in our proofs, and those are going to represent sums of series. I will also say that there are some a sub k plus 1s that we'll also do. So let's say a sub k was 5k plus 3. Could you imagine what you would do for a sub k plus 1? Plug in k plus 1. So that would be 5 times k plus 1 plus 3. In this case, the 5 distributes to the k and the 1, so that's really 5k plus 5. And then plus 3 would be 5k plus 8. Okay, so you can also get an a sub k plus 1, just like you could get an s sub k plus 1. On that one, this is a good example of like, it's important to distribute so that you could add the like terms 5 and 3. Okay, so here's your homework for tonight, and I'm going to give you about 5 minutes. You'll get it done, and then we'll check our answers. If you need a textbook, you can grab a textbook, but I've got the 6 questions on the board, so if you can see the board just fine, you can go off of the board. I will say that the textbook uses P's in this particular portion. Note that when we actually do the work, I'm going to call them S's because they're going to be sums of sequences, series. So I'm going to use S when we do our proofs. Okay, so I don't care if you use P or S. Okay, get to work, you have 5 minutes. if that's the case where I do distribute, because then I can have the one, it wouldn't be two. Okay, you've had about 5 minutes, so now I want you to check your answers on the screen. Let me know if you can't read anything, and let me know if you have questions. I talked to a few people about number 8. Not everybody simplified theirs with the 2k plus 3, but that's an example where I would do that when I show my s sub k plus 1. So I would distribute the 2 and then add the 1 to get 3. Any of those that you have questions about? How I got any of my terms? Okay, then we can move on to proofs. So check that off your list. Your homework is done for tonight. There is a homework assignment for tomorrow. I think it's like 4 or 5 proofs. And you can decide. If you've got really busy times tomorrow and you got a little free time tonight, you could try to get started on the proofs like as far as you can go and finish them up in class tomorrow. If you're busy tonight and you've got more time tomorrow, we'll have some work time in class and then you can finish them up in the evening if you need to. So kind of plan around whatever your schedule looks like. Here is the principle of mathematical induction. So how mathematical induction works. This first slide that I'm showing you and having you write down here, this is like the mathematical definition of mathematical induction. Okay, so it's a little bit wordy, and I'll try to put it into an easier terms to understand here in a little bit. So again, the book uses P sub n just like generally when we're talking about mathematical or inductive proofs. Let P sub n be some statement involving the positive integer n. So you're usually getting something like P sub n equals something, okay, in terms of n, where n represents positive integers. Mathematical induction has 2 parts. The first part is something called the base step. So it's your job in the base step to prove that whatever statement you have, P sub n, it's true for n equals 1. The first case is true, is basically what you're proving right there. In our work with our series, that's going to be a pretty easy step to do. We'll just plug 1 in where we see n and see that it's true. The second part to mathematical induction is the induction step. The induction step is where we say, let's prove that no matter what number we put in for n, so we're going to call any number we put in for n k, the truth of P sub k implies the truth of P sub k plus 1. So K is a placeholder for any number. And if you prove those two steps, if you prove that the first case is true in the base step, and you prove that the truth of P sub K implies the truth of P sub K plus 1, the next thing, then P sub n must be true for all positive integers n. Now, I could totally understand if you have copied this into your notebook and you have dutifully tried to listen to me describe mathematical induction, and yet you look this over and you think, clear as mud. Not very clear at all, right? Okay. So it's a little bit weird at first, and I'm going to, on the next two slides, try to make even more sense of how this induction process is working. In geometry, you would have learned about two types of reasoning, inductive reasoning and deductive reasoning. Deductive reasoning is what you use all the time in your geometry proofs. They're based on facts, theorems, definitions, postulates, axioms, all that stuff. That's deductive reasoning. Because of this definition, this is true. Inductive reasoning is reasoning based on patterns. And so then you can clearly make a connection here as to why we would learn mathematical induction when we're learning about sequences and series, because they're all based on patterns, right? Okay. So we're looking for patterns and we're proving a pattern will continue. Okay, so remember that there's two parts to mathematical induction. Prove the first thing is true, and then prove that P sub K implies the truth of P sub K plus 1. Basically, what's happening here is what we're going to call the domino effect. Have you ever set up dominoes in just the right spot so that when you hit the first domino, all the dominoes go? If you want to waste 5 minutes of time, go ahead and YouTube domino videos. So many cool things you can see with dominoes. On page 635, if you want to reread what the book has to say about the domino effect, you can. But basically, mathematical induction is like dominoes. First, you have to knock over the first domino. You have to make sure it's true in case number 1. If the first domino doesn't fall, the dominoes don't go. Okay. Then your job is to prove that P sub K implies the truth of P sub K plus 1, and it doesn't matter what K is. So it could be the first and the second term, the second and the third term, the third and the fourth and the fifth, the 100th and the 101st term, the 1,000,000th and the 1,000,001 term. That those two terms, consecutive terms, the truth of the one before implies the truth of the one after. Because then, if we know that those two things are true, when our first domino falls, it knocks over the second domino, which knocks over the third, the fourth, the fifth, the sixth, and so on. Okay, so that's proof by induction. If you want to think about it sort of visually, what you're doing there. This is my description of mathematical induction in my own words. So, like, if I'm trying to take apart that principle of mathematical induction that you wrote down, that's what you'd see on the internet, in your textbook, and you're wondering, what the heck does all that stuff even mean? Here's my version of that. On the test on Friday, we're going to give you like a problem to do mathematical induction for a proof. And then there'll be 3 things listed below that, like to set up your proof. Step 1, assume. Step 2. So what's nice about that is it kind of gives you a little reminder about the things that you need to do in order to be able to do proof by induction. So step 1 is what was described as the base step, and your only job in step 1 is verify your formula for n equals 1. So you have some formula. It's going to be a sum of a series. So adding up all the terms, just verify that it works for the first term. You're done. In between step 1 and step 2, we're going to have an assume. Now, it's really important that you make this assumption because your step 2 work will follow the assumption. Also in the assume, we're going to write what it is we want to show, which I'm going to remind you when we do our proof. It's kind of like what you did in geometry when you got a given and a prove statement. You knew where your proof was going, right? Sometimes that was really helpful to know what the end was because we could work backwards. So the same thing is going to be true for us right now. We know what we should get. So can we get there? This is one thing that a few people every now and then are going to take issue with. We're going to make this assumption right after step 1 where we assume that this is true for n equals k. And some people will argue, why do I have to use k? I mean, I don't have a really good answer for you other than that's kind of what we do as mathematicians. And the other thing here is mathematicians are trying to say, we're trying to prove this s sub n. We've plugged in 1 for n, so we know that the first case works. We want to prove that all the other cases work, plugging in all the other numbers, and rather than actually plugging in all the other numbers, that would take me my entire life and I have better things to do, we're just going to do this by proof by induction, and let's just call all the other numbers k, so that they're not n's, they're some different number you're plugging in. So you assume that it's true when n equals k. And then after you make that assumption, you'll also, after the assumption, you'll know what your answer should look like. But step 2, the induction step, is where you do all the work. Okay. So this is the majority of your work in your proof. There's a little bit of work in step 1. But the majority of your work happens here in step 2, your induction step. You have to show s sub k plus 1 is true, and you're going to show that using s sub k plus a sub k plus 1. Okay, and if you can do those two things, then you know it's true for everything. So before we get to our proof example, I want to kind of take a trip down memory lane to your warm-up. Think it was something like -11 plus -7 plus -3 plus 1, dot, dot, dot. And we were adding them up for the first 17 terms. Okay. So we found out that S sub 17 was 357. Okay, so we used the arithmetic formula for that. If I asked you a follow-up question to our warm-up, and I said, what is S sub 18? And you'd already done all the work for S sub 17. So it's the sum of the first 17 terms. And now I want to know the sum of the first 18 terms. We could certainly go back and redo the whole arithmetic formula, but what's another option? You're adding up the terms, so the next term is not necessarily 4. Yeah, so you want to add, if you want the sum of the first 18 terms, couldn't you take the sum of the first 17 terms and add a sub 18, whatever term that is? It is plus 4 to a sub 17, but we don't, we knew what a sub 17 was, I guess, in our example. Okay? But this is modeling this piece right here. Okay? If you knew what the sum of k terms was, then just add one more term, the a sub k plus 1 term, and you'll have s sub k plus 1. So if you try to think about that in context of like if you had numbers, it makes it a little bit easier to understand what you're actually doing. Let's see if we can put this to work. Here's our proof that we are going to do. Now, at any point while I'm working through the proof, if you are like, where the heck is that number or term coming from, make sure that you ask. If you have a question about something, I'm guessing someone else in this room also has that question. So we want to prove that 6 plus 11 plus 16 plus 21 plus dot 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 plus 5n plus 1 is in fact equal to n times 5n plus 7 all over 2. And all of yours will kind of be set up in the same respect. Like you're working with series. Not all inductive proofs are series, but ours are in chapter 9. Okay, so what's really cool about mathematical induction proofs is you get to sound like a real mathematician here. When mathematicians, a lot of times when they start their proof, they need to let everybody know what it is they're talking about. So they start with the word let. Let these things be the case. Okay? So we're going to say let S sub n, the sum of n terms, equal, and then you just copy down whatever you're trying to prove. 6 plus 11 plus 16 plus 21 plus dot 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 plus 5n plus 1 equals, not 5n times 5n plus 7. So that feels like really redundant if you wrote down the problem, right? But like if you're doing your homework, if this is the problem in the book, I would start with my let statement. So now everybody knows what proof we're working on. Okay, S sub n is this sum. All right, begin your proof. Step 1. What is your job in step 1? Verify for n equals 1. Okay, so looking at this whole statement up above, we're trying to verify this formula over here at the end, right? We're saying this is S sub n right here, the sum of all these terms, 6 plus 11 plus 16, so on and so on. So we want to verify that S sub 1 is true. So I'm going to plug 1 in for all those n's. Okay. I don't need to plug it into the middle stuff. I'm verifying the formula is true for n equals 1. So the formula is over here on the right side, and I'm plugging in 1 for n. Well, that comes out to be 1 times 12 in the numerator, which is just 12 over 2, which is 6. Is the sum of the first term in this series equal to 6? Yeah. You see the first term right there, right? S sub n equals 6. If you only had one term, that would be its sum. So we can say, which is true. Verified. Now, I'm always going to be asking you to write inductive proofs for things that are true. So your step 1 should always verify. It should always be equal to that first term. The first term is the sum of the first terms. First term. Okay, so step 1 is done. Next we assume. For the assume step, remember we want to basically test every single number, but not have to test every single number. So we're just going to call every single number K. Like it doesn't matter if it's the 5th and the 6th term or the 20th and the 21st term. We're just going to call it K and K plus 1. Okay, so let's assume that S sub K is equal to, and then you write S sub n with K's in it. 6 plus 11 plus 16 plus 21 plus dot 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 plus 5K plus 1 is equal to K times 5K plus 7 all over 2. So what we're saying is we're testing for n equals K. So we just made a substitution. treat this statement, all of it, like you're given in geometry. If we assume it to be true, then we are accepting S sub k is in fact the truth. But we also would like to know when our proof is done. So I always, after my assume, I write a show that. And this is what I need to show through my math, that S sub k plus 1 is equal to whatever that is when I plug k plus 1 into S sub k. So that's the stuff we were practicing at the beginning of the period. So plug k plus 1 in. For that first k, it's just going to be a k plus 1. For 5k plus 7, when I put k plus 1 in, it's going to get multiplied by 5, which is really 5k plus 5. And then plus 7 will be 5k plus 12. All over 2. Now, if you have a hard time doing like that, simplifying with k plus 1, by all means, like in the margins of your paper, you can write down 5 times k plus 1 plus 7, and then distribute and add like terms. Okay, this walk down memory lane is your proof statement in geometry. So like, how do I know when my proof is done? When I get to that answer. Then I can stop. Then I've proven that the truth of S sub k implies the truth of S sub k plus 1. All the dominoes will fall because I already knocked over the first domino. Okay, so now we're doing step 2, which is the induction step. And I'm going to prove S sub k plus 1 is equal to that thing. But I have to do more than just write it down. Like I have to show the work and prove it. So now I'm taking this k plus 1 and I'm redoing S sub k with k plus 1. So if I were adding up k plus 1 terms, I would start with 6 plus 11 plus 16 plus 21 plus ... If you want to, you can write the 5k plus 1. But this just represents a sub k, right? Okay, because that's up here. It's the k term. And if I want to do the sum of k terms, the sum of k plus 1 terms, then I also need a sub k plus 1. So I need to add an extra term to that. To get a sub k plus 1, use this a sub k rule. 5k plus 1. Put in a k plus 1. 5k plus 5. Plus 1 is 5k plus 6. So it's saying first term plus second term plus third term plus all terms in between plus the k term plus the k plus 1 term. That would be the sum of k plus 1 terms. I don't know what k and k plus 1 are, right? Could be 5th term and 6th term, 10th term and 11th term, 200 and 201. Okay, it doesn't matter. Okay, well, some of that is familiar to me. 6 plus 11 plus 16 plus 21 plus 5k plus 1 all the way up to there, that's all equal to what? 6 plus 11 plus 16 plus 21 plus 5k plus 1 equals k times 5k plus 7 over 2. This is really S sub k. And I assumed that that rule was true. So I can substitute it in for the first k terms. First k terms add up to k times 5k plus 7 over 2. I have to add to it 5k plus 6. So that's like going back to our warm-up example, right? That 357. If we did the sum of the first 17 terms, and then we want the sum of the 18 terms, we could just do 357 plus whatever the 18th term is. Okay? So this little expression right here in your assume, that was your sum of your first k terms, and now you add a k plus 1 term. Well, I'm going to have trouble adding these because 5k plus 6 is like 5k plus 6 over 1. And in order to be able to add, I'm going to need common denominators. So I'm going to multiply this by 2. Well, now I have a common denominator of 2. I'd like to add the stuff that's in the numerator. In order to be able to do the numerator stuff, I'm probably going to have to distribute. Like I'll distribute this k to both terms, so that's 5k squared plus 7k. And then I'll have to distribute this 2, so that's plus 10k plus 12. Which gets me to 5 squared k plus 17k plus 12 all over 2. Okay, so now you have a quadratic over 2. If you look back up at what you're supposed to be proving, show that s sub k plus 1 equals this thing right here, the top of the screen. That looks like factored trinomial. So let me go down here and factor my numerator. To get 5k squared, it must be a 5k and a k. I got to multiply to make 12 in the back, but then my middle terms have to add to make 17. So with this 5 right here, I could use a 1 and a 12. 5k plus 12k makes 17k. Does that match my show that? I'm going to scroll up. I have 5k plus 12 times k plus 1 over 2. Does that match the statement right there? Yeah, is it okay that my two factors are switched around? Sure, multiplication is commutative. So I've shown through all this math, all this long work, that the sum of k plus 1 terms is equal to s sub k plus 1. Thus, s sub n is true for all positive integers n. Now, I will put an exclamation mark of excitement after that, but mathematicians will just put a period. Boring. But I'm excited. We just made an inductive proof. If you want to get started on the homework that's due for Wednesday, you could set up some proofs, go as far as you can. If you're busy tonight, we'll do one example tomorrow at the beginning of class, and then you'll have work time in class tomorrow and finish it up in the evening.